So in this video, we're going to go over how to implement separate chaining. Well, before we look at actual code, I just want to point out a few differences between my implementation and what's in the readings. The main one is some of the routines related to prime numbers. I define them in their own .py file and import them into the hash table implementations. And whereas in the readings, they are part of the hash table implementation, which I think is not the right place for them. Anyway, you don't have to understand them, but if you do, they're kind of fun to read through and understand. And also, I name a few things differently, but hopefully the names make sense, so it's obvious what they mean. So the hash table implementation, the name of the class is hash table SC, stands for separate chaining. We have a couple constants. The maximum number or the initial number of buckets is 97, a prime number, and the max lambda is kind of 1.5. Those are the default parameters to the initializer. They can be changed differently. They can specify differently. However, if somebody initialize a hash table that does not have a prime number of buckets, we find the next one that is bigger than it, and we set it to it. And then also for all the buckets, we allocate each bucket as a linked list. So this might look familiar to some of you if you remember from the sparse matrix. So this is a very similar idea to that. And then finally, yeah, the number of items we start at 0. Okay, and so as usual, the first operation we want to look at is inserting an item into the hash table. So the first thing, well, for any operation we need a hash function, right? Plus the modulo part. So I kind of fold the hashing of the key modulo by the number buckets that's in this one single underscore hash method. And then in the actual insert, the first thing we do, given an item, and obviously we should hash it, so that we to get a the bucket index. And one thing that our hash table does not support is to support duplicate items. So we check if the item is already in that bucket, then you just raise an error. Now, otherwise, we take that bucket and remember that bucket is just a linked list, and we can simply add that item to the head of the linked list. In this linked list, the order should not matter because we expect the linked list to be small. We increase the number of items, and the important thing now is now that we have more items in the hash table, we check the load factor. Right? If the number of items divided by the number of buckets has reached the maximum lambda, then we should do a resize and rehash. And how we actually do that is we make a copy of all of our linked lists first, right? Because the resize is going to actually wipe them out. Now, and then we figure out the new number of buckets. And so what we do, I mean, we can just increase the number of buckets by 1 or 2, but that really doesn't make sense because in that case, we're going to have to do resizing very frequently, right? So we would double the size of the buckets, and then in order to keep the number of buckets to be a prime number, we find the next prime number that's bigger than double the current number of buckets. Okay, and again, this is to ensure we don't do resizing frequently. Okay, and then we do the clear. Remember what happens in the clear is we reallocate the entire list of or array of buckets. And then after that is we go through all the buckets in our copy, right? And we walk through each of the buckets is a linked list, so remember that. And then we take each of the items in the linked list and just reinsert into the hash table itself. So now that we have a insert function, if you know me, I like to test it. So this is the test case, a very simple test case that I wrote. I'm actually going to bring that up in the IDE. This is, okay, test. And now, this is my local little art here is, the separate chaining hash table test case inherits from a generic hash table test. So I'll get to what that is in a bit. But so for here, let's focus on the insert test. So I'm going to just insert a very tiny, the smallest hash table possible with just 2 entries. And the reason I want to start with the smallest one is, like I said, you always want to cover the corner cases, and actually the tiny hash tables, they are probably the hardest to get right. So I want to start with the smallest one, and 2 is the smallest prime number. So anyway, all that I'm doing is, here I want to make sure the number of buckets is 2, and then the length is 0, obviously. And I'm going to insert the number 10 in there. And then I know the number 10, it should end up in bucket 0, right? 10 modulo 2, it's going to be 0. And I want to make sure 10 actually get inserted into that linked list. And then after that, I want to make sure now the size of the hash table is 1. It has 1 thing in there. So let me run this, and it's good. One thing I didn't say about this test is, if you look at it, it does reach inside the hash table and look at what's considered the private attributes. So it's kind of okay in this case because this is a unit test. It can assume certain implementation details. However, it's not good in the sense that if the implementation changes, then we have to change the test. So I'll keep this kind of test to the minimum, and then we will write more generic tests that don't assume implementation details in this test cases. Also, I want to do some simple tests of the rehashing. So I'll insert 3 pieces of data into the hash table that started with just 2 buckets. So I know that it should expand at some point from 2 to the next prime number, which is 5. So the expected number of buckets after inserting these 3 pieces of item is 5. Make sure that's the case, and then also I just kind of go through every data and make sure they are in the right buckets. I'll run it as well, and there we go. It ran fine. The next function we want to implement is contains, so we can check if the key is in the hash table, and it's actually very simple. We find the bucket, and then we just check if the key that we're looking for is in the linked list that's in that bucket. So previously, without the contains method, it was really hard to look inside the hash table to see what's there. But now that we have this method, we can actually write some better tests that do not have to look inside the hash table and assume there's certain implementation of it. So we'll write some new tests that test insert and contains for the hash SC, but they will also work for other types of hash tables. So we are kind of going backwards, I understand. But anyway, so in our hash SC test cases, we actually inherit from the hash table, the generic hash table test cases. So if we look at here, what we actually define is, we have a class attribute as before. You've seen this hash table type. For this, we say it to none because we don't want any assumptions, the type of hash table it is, and we would expect the particular hash table test cases to override this class attribute. So in hash SC test case, it's going to be hash SC, right? Let's see what else is here. Whoops, let me pull up the, yes, generic test. Another thing is just set up the test. You've seen this before. I think that I want to have a deterministic random C, so that when we generate random numbers, they are reproducible. Every time I run the test, the same random numbers are generated, so that, if something fails, I can reproduce the test. Okay, that's that, and then I'm going to actually show the first generic hash table test case I'm going to write is test insert and contain. So basically, I'm going to set up a bunch of data. So I'm going to look at the range for my data is from 0 to 999, but I'm going to just take a sample from that. So I'm going to take 100 of those numbers in the range that's less than 1,000, and then my expected set, it's a set. So I'm going to put the numbers in this set, and this is going to be my my golden set, what I'm going to expect my data to be, and I'm going to test that against my hash table. And again, I'm going to start with a small hash table, and then I'm going to pass all these to the actual test method. And what this test method is going to do is it inserts all the 100 numbers into both the expected set and my own hash table. And I'm going to make sure all of them are in there, so the length is correct. And then all I'm going to do is I'm going to go through all the data. So remember, the data, all data is actually numbers between 0 and 999. And some of them are going to be in the test data and has been inserted, some are not. So I'm going to make sure that when the number, or when the data is in the expected set, it's also in my hash table, and if it's not, then it's also not in the hash table. And that's all that it's doing. And lastly, so coming back to the hash SC test case, I can actually run all of the tests here by doing this. And oops, well, actually, this is good to know. So these are my generic hash table test cases, right? But I cannot run these because I did not define a hash table type. So basically, I have to go to my hash table SC test, and I can run all the test cases here because I actually override the hash table type in here. Now I'm not going to run through all of them yet. We haven't gone through everything yet. Now, if you just want to run one particular test, like for example, want to run the test and insert and contains test, then I actually have to explicitly write that one test that I want to run in here, and then just call the supers same version of a test. So I can just run this one, and yeah, that looks okay. And you can kind of see, we inserted 100 numbers here, so 100 of them, and number of buckets that we use up is 97, so they're fairly evenly distributed, so that's actually good. So the next method we're going to write is the remove method, which is actually very similar to the contain method. We hash the key, figure out the bucket index, we remove from that bucket, that linked list, the key, and then we just decrement the number of items by 1. Now, it's possible that the key does not exist in that bucket list, in that bucket list, in that linked list. But linked list remove, if you remember, it actually raises the error, a key error, if the key doesn't exist. So that's what we want, and that's all good. And next thing, now that we have a remove method, we should write some very basic test for the remove method. In the same strategy here, but so the first thing we try to remove is something that's not there. It should raise a key error. And then if we insert the number 10 and then if we remove it and we try to use the contain to find it, it should be false. Right, so basically, yeah, this is what I have here. I already typed it out, and if I run it, and it's good. So that's just a simple test case for remove. Now I wrote something a lot more elaborate to test the removal, and that actually involves operations like, insert data, remove data, and then reinsert the same data or different data. And the reason for that is they're really used to test a different type of hash table that we'll talk about in a bit. And that hash table has a more complicated way of deleting things. That's why. But it's written in such a way that it's generic and we can use it to test all type of hash tables. So the code is in the file. As you can see, it's slightly longer, but it's kind of commented, and if you want to understand them, it's not that hard to understand. Okay, so we want to wrap up the implementation by maybe thinking about the performance of separate chaining a little bit. So hopefully, and we kind of discussed this earlier, but I just want to summarize it. So on average, the performance should be proportional to the number of items per bucket, right? Which is the load factor. Or if we want to write it in big O of n, then is basically big O of n divided by the number of buckets. So it kind of depends on the number of buckets. If we go to some extremes, number of buckets is 1, then n divided by 1 is n. So that will be O of n, which kind of makes sense, right? If there's only one bucket, it's a linked list, then it's it's O of n. Now, if number of buckets is n, so that means on average each item would get their own bucket. So that's great. That would mean it's a constant time operation. So kind of what we want is that as many buckets as the resources would allow. Okay. Now that's only the average case though. So we hope for the average, but in the worst case, such as a bad hash function, again, we said that before, we can have all the items hash to the same bucket, so the performance is again O of n in case of a linked list of buckets, right? And finally, one thing we should be aware of is that when we reach a certain size and we want to resize the table or expand the table and do the rehashing, that operation is very slow. And you should know what the big O of that is. Okay, so insertion, because this can happen during insertion, so insertion sometimes can be very, very slow.